Morning, everyone. So far in our energy option, we've looked at three primary energy sources. First one was burning of fossil fuels, so taking crude oil, running it through a fractional distillation column, separating it for the carbon chain lengths that I want. One sort of disadvantage of that is burning all these fossil fuels here. Although it does provide the energy that we need to utilize, it ends up producing a lot of carbon dioxide and water products, what we're going to focus more on in today's lesson. Second form of energy was nuclear energy. It relied on this mass defect, as the sum of the mass of the nucleus is actually different from the sum of the mass of the individual particles. As some of the mass gets converted over to energy, both fission and fusion reaction actually increase the average binding energy per nucleon. So it actually gets more stable. That extra energy is radiated away. That one there, typically less sort of carbon dioxide, NO sort of emissions, so there's not that to worry about. But in the different vein here, nuclear products tend to also themselves be radioactive. We differentiated between low-level waste and high-level waste here, and especially spent control rods and things that are really highly radioactive. We really haven't found a nice solution to how to deal with that waste as well. Solar energy so far seems to be the best ideal. Not only is it our ultimate energy source, maybe millions of years ago plants had already absorbed the solar radiation. That's what we're currently utilizing as our fossil fuels. But we saw how we can actually harness the solar energy here, use this conjugated system. We're going to design photovoltaics that are sort of mimicked based on what plants do as well. So that mimic that sort of coordinated, conjugated system. The longer the conjugation, we mentioned, the higher the wavelength that's actually absorbed. And remember, we see the color transmitted that's opposite, that's complementary to the wavelength that's being absorbed. Today, we're going to take just a quick sort of global scale impact here. We're looking at, especially when you do burn these fossil fuels here, we're going to talk specifically about the greenhouse effect and sort of what are potentially these chemicals doing in our environment. Sure, global warming is a sort of a controversial sort of issue, but in today's lesson, we're just focusing on the chemistry that we're sure of. We're going to talk about the greenhouse effect being a very natural consequence. It happens normally, even if it weren't for burning fossil fuels, but we're just going to focus more so on the chemistry behind how the extra carbon dioxides and the extra waste products that we're throwing in our atmosphere, how might it be having a contribution to potentially one factor for global warming. So let's have a look at the environmental impact on global warming. First big idea here is we're going to talk about greenhouse gases. So far we've seen greenhouse gases like water, like carbon dioxide, different nitrous oxides, sulfur oxides. These greenhouse gases typically allow incoming solar radiation. Now, solar radiation comes to us in a whole range, but what they're emphasizing here is it's usually shorter energy rays that get all the way through, but they end up absorbing the long-wave radiation that reflects off the Earth. Some of this absorbed radiation is re-radiated back to the Earth, so we're going to get a nice picture of this on the next slide here. This is just a natural greenhouse effect. So solar radiation, so radiation from the sun, it comes to us high energy, short wavelength. Most of it's able to get through our atmosphere no problem. It reflects off the surface. Now, terrestrially here, the Earth sometimes absorbs some of that radiation. It's not all of it that bounces off. We call this now terrestrial radiation because this is now reflecting off the Earth's surface. And when it gets reflected off, it typically is more longer wavelength and lower energy than what it come in. Now, again, I want to emphasize here, this is naturally happening. We have an atmosphere that constantly is letting solar radiation through, and it is letting a lot of that terrestrial radiation out as well. Now, sort of the next picture here is we're going to find some of that solar radiation because we have our atmosphere. Some of it never actually ends up reaching the Earth's surface. It gets reflected off right away. We don't see any of that. So there's that reflection there. What we're more interested in, however, is some of the solar radiation is absorbed, some reflects off the Earth's surface. So that's just specifically looking at the radiation from the sun itself. And then what we're going to focus on here is more so the terrestrial radiation here. It is true, some of the terrestrial radiation does get through, but here's the part that we're worried about is the terrestrial radiation at that longer wavelength, they reach the atmosphere and the atmosphere actually absorbs it or re-radiates it, re-reflects it back to the Earth's surface. And you can imagine this process happening time and time again and potentially leading to higher than normal radiation on the Earth's surface. So we call this one here the greenhouse effect. What I want to emphasize here is this is a natural phenomenon. Regardless if we burn fossil fuels or not, this would normally occur. this is actually good for us because it helps us maintain an average surface temperature here of roughly about 15 degrees. It doesn't let our planet get overly cold or overly hot. Doesn't really matter the seasonal variations, things like that. It allows for life because it's relatively warm enough. Now, just putting some numbers to this in here, just a quick rule of thumb here, we can say 75% of the solar radiation is transmitted. It gets through the atmosphere, no problem. 75% of the Earth's, the reflected terrestrial radiation, however, gets absorbed, sort of re-radiated back towards, so it doesn't actually leave the system, and it gets re-radiated, reflected back towards the Earth's surface, causing this greenhouse effect. Why it's called the greenhouse effect is we actually design greenhouses exactly in this design here. Instead of just letting the atmosphere passively do this for us, we design greenhouses with planes and planes of glass, which are purposely designed to re-radiate some of the radiation, some of the heat back to inside the greenhouse, and we can actually create a natural environment here to actually grow our crops better, especially when the weather's not nice outside. We can actually sort of mimic this global greenhouse effect here on a much smaller scale. So some sample examples of greenhouse gases here. So we have long-lived greenhouse gases like CO2, like methane. Different layers of the atmosphere contain different amounts of them. So we have the stratosphere, the troposphere as well. We have other components here. Let's see which one we're going to highlight here. Greenhouse gases will cause this greenhouse effect. It is believed to be one factor of global warming. You can debate on that issue, but again, we're focusing mainly on the chemistry aspect of it. And then what we're going to see is it's not all doom and gloom. It's not all, oh, it re-radiates, it's getting hotter. We're going to actually find that sometimes we actually have particulates. So clouds, when they have rain droplets, when they have different chemicals inside them, those aerosol material, that smoke and dust, actually forms particulates. And this one would actually reflect sunlight away from us as well. It's just that normally if we trace through the data here, the amount of scattering here is not as great as this greenhouse effect and this warming. So even though this could refer to it as a global dimming process, there are some years, I think they say in 1960, there were a lot of volcanic eruptions, and basically there was a lot of soot and a lot of particulates in the air that a lot of the solar radiation got reflected off, and that the average temperature in that year actually decreased. But it's just steadily, except for that year, steadily over time, the overall temperature has been increasing. It doesn't seem like much. Maybe it's only been increasing like a degree or two over decades and decades, but it is definitely significant. It is definitely changing the sort of biological patterns, different ecosystems, and it's believed to be one of the factors causing global warming. So here's a nice satellite image of those gases here. Remember, it is a global problem, so whether it is sort of first world nations that do a lot of burning of fossil fuels, it's not just we have to contend with the CO2 that we toss in the atmosphere. The CO2 actually gets blown around, so it can be devastating for the entire world. So that's why it's going to need a sort of international cooperation to sort of address. The chemistry, again, we're going to focus on here. If we look specifically at molecules like carbon dioxide, like water here, how do greenhouse gases absorb this lower energy radiation and re-radiate it back? We talked about this in our spectroscopic chapter here. Covalent bonds are not static. Covalent bonds, we know, are electrons that are attracted by the positive nuclei on both sides. There's a compromise between the nuclei want to get close to the electrons, but they don't want to get too close to the other protons. So there's going to be that compromise giving you this bond length. Covalent bonds, we use that spring model, and they're constantly bending and stretching and warping. If I'm diatomic, I just have the stretching motion here. But if you think of a molecule like water here, we have a lot more different choices. So we did our water dance here. You can actually change your bond length, so shorter bonds, longer bonds. You can change your bond angle. You can twist, right? So you can spin around an axis. You can just transverse motion. You can actually move around. They're actually showing you for the water molecule some other different modes that you can actually vibrate. Each of these modes here will be sensitive to IR radiation. So if you did IR spectroscopy, you can actually find peaks for each of these particular wave numbers. So they demonstrate other more fancy motions here. The scissoring motion when both arms get pulled together, twisting, wagging, rocking, torsion. You don't need to know the names of all of these ones here, but the emphasis here is you need to note it is specifically we're looking at covalent bonds, and specifically if I have a dipole moment. Specifically, it has to be a polar bond that absorbs IR radiation. So if I look at a carbon dioxide molecule as an example here, carbon dioxide, we said overall is nonpolar. overall, we look at the bonds separately. O wins on the right-hand side, O wins on the left-hand side. Those dipoles cancel out. Those polarities cancel out. No one actually wins. But do we have polar bonds? Definitely. When I look at just the carbon and oxygen, the oxygen side wins. The oxygen side is kind of negative, partial negative. The carbon side is kind of positive. And what's going to happen here is when IR radiation comes in with the right frequency, even though overall we were nonpolar, when we consider the entire thing, it cancels out. Those IR radiation is sensitive to the springs here stretching and contracting. Anytime we have a potential dipole, it is IR sensitive, and the IR radiation can actually change the dipole moment. That's a really important phrase for you. Make sure you note it is IR radiation that gets absorbed because it changes the dipole moment, even though your overall molecule might, like CO2 here, be nonpolar. So greenhouse gases here, they absorb the infrared radiation. This is terrestrial radiation that bounces off the Earth's surface. They get excited to a higher energy level. They stretch and they start bending a little bit quicker. And then what they end up doing is they end up re-emitting this radiation back towards the Earth's surface. They can then relax to a lower energy level. And what we have is sort of, if you look back at the data here, from the 1800s to 2000 or so here, this is just plotting for you the average amount of CO2 in the atmosphere. So we started off from parts per million about 290 or so, and over the course of the last 100 years or so, we see that we've gone up almost 50%, right? A lot more carbon dioxide, and this is a direct consequence of burning fossil fuels. So there's a lot more CO2s. Each of those CO2s here is IR sensitive, so we have a lot more particles that might potentially be able to absorb that radiation. When we sort of plot this graph here with the global temperature increase here, again, this is just over the last 40 years, so when we actually had a lot of good data to base it off of, we can actually plot it against the average carbon dioxide concentration going upwards, and we see while there are seasonal fluctuations, while it's like warm and cold as we get through summer and winter times here, we have a steady increase in temperature. So this correlation is what's believed to be because there's so much more CO2 that's causing more of this IR sensitivity, IR radiation being absorbed and then re-radiated back, and that's causing, and it's one factor that's influencing potentially this global warming, this global temperature increase. In fact, this can be extended over, if you look back at the last 100,000 years, 200,000 years or so, if you believe sort of ice core measurements and actually sampling as you dig deeper into the ice core, you're actually digging deeper in time. If you sample the CO2 amount in different layers of ice here, we see this sort of steady change here. 400,000 years ago here, we had the carbon dioxide. Sure, there were natural fluctuations over 50,000 years or so. So that is definitely well documented here, but you see sort of the correlation matched up with it. The global temperature seems to correlate very quickly. Again, not by much. It's only within the span of, let's say, 5-6 degrees or so, but enough to cause huge devastating consequences for us. So again, the concern here is if greenhouse effect, if the extra carbon dioxide we're tossing in the atmosphere here is a factor that's resulting in our global temperature increase. We have a bunch of different models here. The worry is with so much more CO2 that we've been tossing in the atmosphere, as the CO2 concentration goes up, maybe the global temperature is going to go way up as well. So depending on the different models, again, different models here will factor in different considerations, things like that. But in general, regardless of the model, they have the names of these models. You can look in more detail, but you see gradually there might be this is just prediction that there will be a steady increase in temperature there. So that there, again, we're focusing on the chemistry. We're focusing on potentially one correlating feature that's causing global warming. Let's look more at these greenhouse gases in a little more detail. The primary greenhouse gas I want you to say is actually water, and that actually owes to its abundance. There's most water that comes just from natural evaporation from the oceans. Remember, greenhouse effect is a natural effect that happens on the Earth. Water, carbon dioxide, and methane here. Carbon dioxide from burning our fossil fuels. Every time we run through a combustion reaction, we end up releasing CO2, whereas methane from farming here tends to be released as well. Each of these has what's called a global warming potential. Your textbook calls this a greenhouse effect, doesn't matter the name of it. We set CO2 as our standard. We say it has a global warming potential of 1. In this case here, when water has a global warming potential or a greenhouse effect of 0.1, that means that water has 10% less of an impact on the overall global warming than CO2. whereas one molecule of methane is 30 times as bad as CO2 in terms of its global warming potential, in terms of its greenhouse effect. Depending on what you look at, you might argue, well, methane here, in terms of its abundance, it's not as common. It's only attributing to about 5 to 10%, although molecule for molecule, it's actually really, really bad. Whereas carbon dioxide actually influences more, 10%, 20%, or water more, 47%, even though they have a relatively low global warming potential because there's a more higher abundance of them in the atmosphere, the overall contribution might actually be higher. So these are not the only greenhouse gases. Again, this is a natural phenomenon. It's just we're worried about in our industry, in our sort of anthropomorphic sources here, are we artificially increasing these much higher than they would have been normally? We're going to focus on some of the effects of these greenhouse gases, regardless whether you believe global warming or not. So these are some consequences you can list off. Steadily, our oceans are becoming more and more acidic. We talk about as the global temperature rises, the ice caps and polar glaciers there are melting away, so the sea level is actually rising. This is going to result in changes to agriculture, changes in biospheres, ecosystems, biodistributions where creatures can live, as well as more frequent extreme weather. So let's take a look at some of these in more detail. So ocean acidification here, when we consider this CO2 in the atmosphere here, CO2 in the water, first thing you need to emphasize is there's a natural, we call this a heterogeneous equilibrium. So this is already occurring. There is CO2 in the atmosphere, there is CO2 in the water that's dissolved, that's been soluble into the water. There's an equilibrium. Doesn't mean 50-50, doesn't mean it has to be equal proportions. You have to look up the K constant for that physical equilibrium there. But basically what happens here is if we happen to have too much CO2, the increase in CO2 will end up shifting the equilibrium, will end up getting a shift towards having more aqueous, having the CO2 dissolve better in water. So in that case there, CO2 naturally serves as a carbon sink. It stores the carbon. It doesn't let the carbon dioxide in the atmosphere be too high. However, with gradually warming of temperatures here, we're going to find that as the temperature increases, CO2 becomes less and less soluble in water. In that case there, if I can't, carbon dioxide, aqueous was supposed to be my carbon store. If I can't absorb as much carbon dioxide, that's going to then shift the equilibrium. It's going to then re-release the CO2 back into the atmosphere. There's less CO2 that's absorbed from the atmosphere, and now CO2 in the atmosphere can result in that greenhouse effect there. Not only that, when you actually take a look at some of these equilibrium reactions here, because CO2 here is a non-metal oxide, when it hits water, we're not surprised it ends up forming acidic solutions here. This carbonic acid is a weak acid. It either protonates once, releasing off H+, or bicarbonate, releasing off H+. Steadily, as you affect this equilibrium, you're going to be affecting how much carbonic acid is produced, and steadily the oceans are becoming more acidic. So that's the ocean acidification consequence here. We can explain that with sufficient chemistry. You do want to memorize these equations so you can quote them if they ask for it. There is a steady sea level rise here. So basically, we mentioned here as the polar glaciers and other ice deposits are melted, the water level is going to go upwards, and also water as a liquid actually occupies more volume. So there's also a slight thermal expansion as well, both of which causing a sea level rise. So here's another model of just sort of the sea level, the mean height of the water. These models here predict from where we are now, like 2008, a little bit outdated here, but we're gradually expecting this one here to steadily rise by some 20 centimeters, 40 meters or so globally. So not just in individual areas, but all over. It's not all doom and gloom, however. So if we know CO2 might be a factor that's contributing to global warming, what we can try to do is we can try to control our CO2 emissions. We can try to design cars that are more fuel efficient, that although we might still need to burn fossil fuels and you might need to still be releasing carbon dioxide, hopefully the more efficiency, you're getting more energy versus how much gasoline you're burning. That would limit the amount of CO2. The increased sort of push for more alternative and renewable energy sources, so decrease your reliance on oil or fossil fuels. You can do more political or market-based control. You can put taxes on carbon. You can try to deter people from relying on just oil dependence too much. Or we can do what's called carbon sequestration here. Sequestration is a fancy word for capturing carbon here. I don't know if this picture shows very much here, but basically it's saying where we sort of harness the oil here, we end up releasing a lot of carbon dioxide. If before we end up leaving letting those gases just naturally float out into the atmosphere. If we have scrubbers and things that can absorb and collect that CO2, we can store those carbons as carbon solid instead of letting the CO2 just escape into the atmosphere. So again, let's take a look at some of the textbook slides just to qualify some of this information, but at least that's an overview of some of the big ideas here. Okay, so let's have a look at what your textbooks have to say about this. So regardless whether you believe in global warming or not here, again, we're emphasizing more so the chemistry behind this natural greenhouse effect here, and we're trying to, if it is potentially one factor that's causing to a global temperature increase, what are things that we can do to sort of minimize that change there. So if you just scroll your way down here for greenhouse effect, we're looking at the section here, C5 on global warming. Again, I want to emphasize here the greenhouse effect here is a natural phenomenon. Okay, some people are saying, well, because it naturally occurs, that's why it's not a global warming feature. It is a natural phenomenon. However, what we're worried about here is it's our human activities that are increasing. We're making it more dramatic than otherwise would have been. We talked about how this solar radiation gets reflected back. They like this terminology here of basically that terrestrial radiation that bounces off the Earth's surface, it gets absorbed by IR-sensitive molecules in the atmosphere, and it gets re-radiated, right? They prefer that language versus reflected. So just re-radiated back. Naturally in our atmosphere, the most common greenhouse gases are water and CO2. Water because it's about 50%, 60% of our atmosphere. But again, the emphasis is when we've been depending on oil and burning fossil fuels, we've been dramatically increasing the CO2 way more than what we had previous. Remember, the molecules that are IR sensitive have to have a dipole moment, so therefore they're saying if I have a symmetric molecule, a diatomic molecule can't absorb IR radiation. The thing that allows it to absorb IR radiation, make a note to yourself here, is ability to absorb infrared here. It's this phrase here, there has to be a change in dipole moment, which means you have to have a polar bond. So CO2 is a good example of this one here. Although CO2, you might say, back in chapter 4, it's nonpolar. However, we do have polar bonds. I don't care that overall you're nonpolar. Because I do have a polarity, I do have a dipole moment. If the IR radiation comes in with the right frequency, or in spectroscopy, if I send in all the IR radiations, this will be sensitive. It's going to start stretching and contracting more when it's the right IR radiation. It can then absorb this radiation, not letting it go out, and it can, once it's done, when it relaxes, it can then re-radiate this back to the Earth's surface. So greenhouse factor, so they call this one here a global warming potential on the slide. Doesn't matter what name you give it. So global warming factor. Global warming potential, I think they called it. And basically it sets carbon dioxide as a global warming potential of 1. And it says, it compares to the other ones here. So one methane molecule, dollar for dollar, it's actually 30 times worse than it. So global warming potential of 30. Whereas if I have a greenhouse factor of 0.1, I actually need 10 water molecules to be similar to a carbon dioxide, global warming effect as carbon dioxide. Make sure you can list off some consequences of a mean increase in temperature, globally speaking here. It changes our agriculture, it changes our biodistribution, losses of habitats, things like that. So the key features that we talked about, because we are melting polar ice caps, things like that, there is going to be rising sea levels. So we need to worry about, as the water level increases, where are places that are low-lying elevation and actually look out for those areas. So that can be causes for more floods in areas, more extreme weather conditions. This second one here is an important one here because we talked about here, so you can draw the picture for yourself, CO2 as a gas and CO2 aqueous, they are naturally in equilibrium. So carbon dioxide in the water actually acts as a carbon sink. It's just that, like we saw, as we increase temperature, solubility decreases. So less CO2 can actually be dissolved, so therefore we're going to end up having more CO2 in the atmosphere, and we sort of lose that capacity to be able to sink out and actually capture some of that carbon. Having more CO2 here gradually actually shifts the equilibrium the other way as well. The CO2 here I mentioned is a non-metal oxide and ends up generating carbonic acid, where it ends up acidifying the oceans, and that actually inhibits sort of marine creatures, marine organisms as well. So those are two consequences here. We talked about here having more extreme weather conditions. So some other consequences for this global impact. On the next slide here, we're going to have a look at, just want to find the other the other consequence here was just the changes in biodistribution. So those are the four. So on the back side here, we have another consequence. We do this phrase here. It's sort of the opposite of global warming. It's called global dimming. And in this case here, we're looking at soot particulates. Specifically, we're usually looking at clouds. So clouds, depending on the material that those clouds have, depending on the humidity, how much water is in there, they can actually scatter light so that the less solar radiation actually reaches the Earth in the first place. So in the 1960s, we actually had so much soot and so much particulates, we actually reflected a lot of the solar radiation that the global mean temperature was actually lower. Now that was a sort of extreme case here. It was just 1 year in the midst of many, many years. Steadily, though, if you look at the data, it's just been gradually rising. So if you look at sort of incomplete combustion, so incomplete combustion typically it's partial combustion because you don't have enough oxygen. So not enough oxygen, and it ends up releasing a dirtier flame of carbons and carbon monoxides, unburned particulates here causing this reflection. Pollutants reflect the sunlight back into space. They're more reflective than unpolluted clouds, which have more water droplets. Again, as I mentioned here, it's not all doom and gloom. There are some strategies that we can look towards to try to minimize our CO2 levels. We can try to improve the efficiency. You might still need to travel. You might still need to depend on fossil fuels, but if your engines can convert the energy better, it can maintain more of it as useful energy. We can decrease the amount of CO2 that we end up burning off. You can also reduce the amount of use that you do. Use public transit more, other modes of transportation. Electrical vehicles, the idea. Although the thing with electrical vehicles, sometimes when you actually design the batteries and we design the systems, maybe in creating that electrical energy, it also is resulting in a carbon footprint. So it's just a matter of where the carbon dioxide is actually being released. So overall, it's still a good idea, though. If you can rely more so on alternative sources, renewable sources, it decreases our dependence on oil and other fossil fuels. Let's harness more of that solar radiation. We'll see more with photovoltaics, geothermal, hydropower, nuclear power. If I can more safely use it at a reduced speed, it reduces the dependence on a carbon fuel. And lastly, they use that word here of carbon sequestration. Remember, sequestration just means capturing the carbon dioxide, storing it before it actually gets burned off. Instead of actually being burned off and actually forming CO2, I may actually capture it in the carbon solid form and actually just bury that carbon. Or if I have CO2, I can have stores of carbon dioxide. Maybe I can get solid carbon dioxide, like dry ice. I can capture it before it actually just vaporizes into the atmosphere. So leave the lesson off there. Hopefully that sort of indicates to you more sort of global impact as you look at some of these energy sources. There's just a little bit more to go in the energy option. We're going to switch over to rehash a little bit of electrochemistry, and then we're going to come back at the end to take a look at semiconductors and take a look at how do photovoltaics actually convert the energy mimicked after plant photosynthesis. Thanks, guys. Take care.